Okay, so we're going to take a look at when we have to separate the variables and solve a differential equation. Okay, so this is specifically when we have something in terms of y and x for our derivative. And so what we want to do is we're going to divide by f of y, right? And leave g of x on the one side, move the dx over to the other, and then we take the integral of each side. Okay, and then we're going to have our plus c and go from there. Okay, so this is a review lesson from last year, so feel free to pause it and just try the problems on your own, fast forward, whatever works for you. Okay, so we are going to solve this initial value problem and indicate the domain over which the solution is valid. So first thing we're going to do is we are going to move the dx to the other side. And now we want to move the y to the other side, so we'll just multiply by y. Okay, the only way we can get rid of a differential, meaning the dx and the dy, is to anti-differentiate. Okay, so we're going to integrate both sides. Here we get y squared over 2. Technically there would be a plus c, but we like to just keep it on one side. Then we get x squared over 2 plus c. This is where we're going to take our initial value. So we have y equals 1 when x equals 4. So we're going to substitute in. So we're going to have 1/2 equals, so 4 squared. So we're going to get 16 over 2, or 8. I'm actually just going to leave it as 16 over 2. So I have my common denominator. So therefore we get c is negative 15/2. Now we go back to our y squared over 2 equals x squared over 2. Replace the plus c with the minus 15/2. And the last step is now we just want to isolate y. So we have, right, we can get rid of all the 2's. So y is going to be plus or minus the square root of x squared minus 15. Now, we're not going to have both of those. Remember, what we want to do is we want to go back, just make sure our initial condition is true, and that's not going to be true for the negative in front, so it's just going to be y equals the positive square root of x squared minus 15. Okay, last thing we want to consider is the domain. So in this case, we have a square root, so we want to make sure that x squared minus 15 is greater than or equal to 0. So this is going to be true when we have negative infinity to negative root 15 and positive root 15 to infinity. Okay. Again, if you want to pause it and try the next one on your own and then see if you get the same answer. Or we can just follow along. Here I'm going to do the same thing at the same time. I'm going to move the dx over and get the y squared divided. I'm going to write that as y to the negative 2 dy. And this is going to be 1 over x dx. Integrate, integrate. So we're going to get y to the negative 1/2 over negative 1, or negative 1 over y. And this is going to give us our natural log, absolute value of x, plus c. Now we go ahead and plug in, well, when x is 1, so that's going to make natural log of 0. Plug in y is negative 1, so that means we get 1 for c. Okay, so now we're going to go back to the negative 1 over y equals natural log of x plus 1. And then I'm just going to rewrite that as negative 1 over, oh, I didn't mean to put the plus c. Sorry about that. That should be our plus 1. And we have natural log absolute value of x plus 1. And we just need to make sure. So this is going to be true for all reals except for x cannot be equal to 0. Okay, law of exponential change. This should look familiar, right? If y changes at a rate proportional to the amount present, so in other words, dy dt equals k times y, the solution to that differential equation is our y equals y naught e to the kt, where k is that constant growth, right? Or decay, depending on if k is positive or negative. Okay, we also have it with money, but we never really do much in AP class with money or, loans or things like that. It's almost always like a bacteria growth or population growth, and that's why I like to stick with the y equals y naught e to the kt. Okay, population grows according to the equation dy dt equals ky, where k is a constant and t is measured in years. If the population triples every 10 years, what is the value of k? All right, so again, this whole thing, dy dt equals k times y, I don't need to do anything. I mean, you can go ahead and solve it the long way, right? Or just know this implies y equals y naught e to the kt. All right, so we know it triples, so the value is going to be 3 equals e to the 10k, right? Kind of like half-life, but this is tripling, so remember, we don't really need that y naught or the y value because you'll always get 3. Okay, next we're going to do natural log of both sides. That's going to give us natural log of 3 over 10 for k. You can leave it like this, you can change it to a decimal, but when we're actually working with the problems, we always want to use exact, store that value of k. So if we want to find the population in, 18 years, then we're either going to leave it as natural log of 3 over 10, or like I said, put it in your calculator, but store it. Okay, our famous epidemic, certain epidemic, the number of people that are infected at any time increases at a rate proportional to the number of people that are infected at that time. This whole sentence just tells us dy dt, right? Number of people, that's our y, right? At any time, that's our dt, is proportional to, right? So that's our k times y. So if 1,000 people are infected, when the epidemic is first discovered, and 1,500 are infected 7 days later. Okay, so we got 1,500 is our y, 1,000 is our y naught, and this 7 days later will tell us how we're going to isolate for k, find that rate. So we'll divide, this is going to be 3 halves equals e to the 7k. Take the natural log of both sides. So we get natural log of 3 halves over 7 is our value of k. Okay, so we want to know now how many people are infected 14 days after the epidemic is first discovered. So you could either do 7 days after the 1,500 or use the initial amount. I'm going to use the initial amount, and I'm going to use natural log 3 halves over 7 times 14. This actually you can actually simplify this by hand. Do you think about the properties of logs, right? So this will be e, and then that'll be 2 natural log of 3 halves. Well, that's just natural log of 3 halves to squared, which we could rewrite as natural log of 9/4. So notice the e in the natural log will just become 1,000 times 9/4. And we get 2250, and that's going to be people. You, of course, can use your calculator as well, and you'll get the same answer. All right, and you have the worksheet for homework.